Hello, math analysis students, and welcome to just one problem today for homework. I want to introduce you to an application of some of these cubic polynomial functions we've been dealing with. So we're going to use what you've learned about finding roots and whatnot to help us solve this problem. It says, this is number 8 in the handout today from class. A manufacturer cuts squares from the corner of an 8 centimeter by 14 centimeter piece of sheet metal and then folds the metal to make an open top box. Okay, so this is a very typical problem in this unit. These cutting squares of uniform length, it should say. Okay, but yeah, the squares are assumed to be of uniform length, uniform size from this piece of sheet metal. So this side I made smaller, call that 8 centimeters, and the other size was 14 centimeters. So what we have now, guys, we've got part A says express the volume of the box as a function of x. So volume is three-dimensional, all right, and that's how kind of we're going to have to incorporate a cubic polynomial. All right, so what you want to first do is think about ways to express the length, width, and height, which is the product of those three is the volume of the box in terms of the variable x. So the x is the length of each square. All right, and again, the volume is length times width times height. And in terms of, or as a function of x, the length is going to be, well, if each of these is x and the whole thing is 14, well, it's going to be 14 minus 2x. 14 minus this x will be the distance from here to here, which after the corners are folded up, that will be the new length of the box. Okay? So for this side, it's 14 minus 2x, that's the length. 14 minus 2x is the length. It'll always be minus 2x because you'll have two lengths, two x's cut out. And this side, as you might guess, is going to be 8 minus 2x. That's going to be the width of the box. And the height of the box is just going to be x. When we fold up these squares, that is going to be the height of the box will just be one of those x's. So this is the answer to part A. This is a function, the volume as a function of x. You don't need to expand this. You could expand it, but you don't need to do that. Okay? We're actually going to kind of quit expanding the polynomial factors for a little while, unless I ask you specifically to expand it. You're not going to have to do that for a little while. All right, so that's part A, the volume as a function of x. Letter B says, what is the feasible domain of the function? Okay. This is where we've got to do a little work like we've worked on recently. The feasible domain, meaning the x values that would produce positive y values. The x values that would produce positive volumes. Okay, if we use an x value of like 10, for instance, we'll get a negative for the volume. That's not going to be in the feasible domain. Okay, so the feasible domain just applies or just refers to x values that produce positive y values. The way you find that is by finding the roots, first of all. So for part B, you want to list the roots. If 14 minus 2x is a factor, we would set that to 0 and solve it, and we get 7 is a root. If 8 minus 2x is set to 0, we get that 4 is a root. And the last one, of course, if x is a factor, 0 is a root. So let's write these in order. 0, 4, and 7 are the three roots of this volume function. Okay? So what we're going to do is we're going to graph this to help us see the feasible domain, all right? Because it's going to be between either 0 and 4 or 4 and 7. It's going to be our answer. And we'll check the graph to see which one of those it is. All right? So this is a positive. Negative 2x times negative 2x would be positive 4x squared times positive x. It's going to be a positive cubic. Now, look over here. That's the way the positive cubics look, right? So if we're graphing this, here are our roots, 0, ballpark it, 4, and 7. And it's a positive cubic, so it's going to look like this, right? Something like that. What we want to find is, again, the region of x values that produce positive y values. That's going to be our feasible domain. So y is positive between here and here, between 0 and 4. Okay? So between 0 and 4, it's going to be our feasible domain. All right? Right in there is where the y is positive. The y reaches a relative maximum right there. Okay, so that point there, whatever x and y are at that point, those are going to be the measurements we would want to use to maximize the volume, given these size restrictions. Okay? But between 0 and 4, between these two roots that produce a positive y value, is our domain. So the answer is bracket 0 to 4. Okay? You could also write the set notation. 0 is less than x is less than 4. Right? In fact, we probably should use parentheses and not brackets because x couldn't be 0. We wouldn't have a box. Or we wouldn't be able to, it would have no height. So actually, I'm going to run out of room here. The domain, I'm going to write as in set notation for now. Okay, but I'll also write or 0, 4 with parentheses. Because we can't include 0 or 4 for that matter, because then we wouldn't have a box. All right? Right, if x was more than 4, this side would be 0. It would be 0 or a negative. So x can't be more than 4. Right? So, regardless. So far, we've written the function based on length times width times height. I found the roots, which were very easy to find because we already have this factored. And the last part is something definitely new. It says find the approximate value of x that maximizes the volume. All right, then find the maximum volume itself. So the way we do this is by a calculator. Okay, I don't have one handy just to show you right now, but I can tell you that I can show you exactly what to do. First of all, here's a big one. All right, we're going to want to start by hitting second calc. Now this is assuming we already have typed in the function into y equals. You would hit second and then calc, okay? And what you would then see is a list of possible choices. You want to choose the maximum, okay? In this case, it asks you for a maximum. I might ask you for a minimum also, but in this case, it asks you for a maximum. So I think it's the fourth choice. So select the maximum, and then you're going to see the graph appear. From the graph, it's going to say left bound. Okay, what that is asking you for is you're going to want to find the maximum here. So when it says left bound, all you really have to do is choose some x value to the left of what you think this point, the x value at this point is. This point might be like 1 or 1.5. So what I would do is I would always just choose the first root. When it asks you for a left bound, it's safest just to choose the root that's to the left of that maximum point. So it says left bound, I would type in, so L left bound, I would select or hit the number 0 and then enter. Okay? And then it'll say right bound. And then you want to select 4 and enter. Okay? So you select the 0 as the left bound, 4 as the right bound. What you're telling the computer to do, calculator to do, is to give you the highest y value on that interval, or the x value that produces the maximum point on that interval. Okay? Then you hit enter again. Make sure you hit enter again. And then on the bottom of the screen, it will say x equals, and you want to round this to the nearest thousandth, x equals 1.639, and then y is approximately 82.981. Okay? Now, those are essentially your answers to part C. All right? So it tells you the x value, the value of the side of the square that will produce the largest volume, right? Volume is y in this case. And y is that volume itself, okay? So the y value is always going to be sort of the most important, right? That's going to be the maximum volume that we can attain given the restrictions, right? So we're going to do more problems like this with both area and volume, okay? Area is just two-dimensional, so we don't really need a calculator. But regardless, just to review, it's important to know how to draw the picture, although sometimes it will be drawn for you. And this whole process we do in order to find out maximum volumes. Right? So we write a volume equation, we find the roots, and that lets us know the feasible domain. We use the feasible domain to know, okay, what number do we use for the left bound, what number do we use for the right bound when we're using the calculator to find the maximum. Okay? So hopefully this was easy to follow, and you can always come back and watch it again.